She received her BA in physics from the University of Chicago and her PhD in the applied physics with a minor in biology from the California Institute of Technology. She is currently the Ray Irani Chair of the Engineering and Material Science and a Professor of Chemical Engineering and Material Science at the University of Southern California. She is the Director of the 2 nanofabrication clean rooms, the W.M. Keck Photonics Clean Room and the John D. O'Brien Nanofabrication Laboratory. She is on the editorial board of ACS Photonics, APL Photonics, and Optics Letters. All the 3 generals are very renowned in the field of optics and photonics. The World Economic Forum Expert Network, a member of the Sigma 11th and NAI, a senior member of the IEEE and AICHE. She is also a fellow of the Optical Society of America and SPIE. She is also the faculty advisor of the USC SPIE OSA Joint Student Chapter. Is a chair of Micro Resonators Conference at Photonics Best LASC, as well as a committee member of the several other conferences, and is a member of DI committee. So with this introduction, I welcome the Professor Andrea and request her to deliver her talk. Thank you.
Thank you very much for the warm introduction, and it's always a pleasure speaking to student chapters, being the advisor of our student chapter, because I know how hard all of the students work to make a successful chapter. So today I'm going to speak about some of my lab's work, working on integrated photonics. But first, I will give a brief introduction to the big picture vision of the work that our lab is doing in the field of integrated photonics, as well as bringing material science into integrated photonics and developing new devices. Before I begin, I want to thank all of the graduate students and postdocs and undergraduates who work in my lab. They're the ones that really do all of the research. I just get the privilege of presenting it. Specifically in this effort, I want to thank Andrea. He's a current student who's really been contributing, as well as Jinghan and Yingmu. They've really been kind of spearheading this research efforts. So in our lab, we really work over kind of 3 length scales. We begin any project with developing a new material, whether it's an organic small molecule that's light emitting, or a nanocrystal material, or thin film. And we try to optimize the optical properties of the material for a potential integrated optical device. And this could be something like a waveguide, coupler, resonant cavity, and it might be the device is completely developed out of that material, or it might be a coating on the device. And then that device could kind of move on to the next level, and maybe it's used in an integrated system, or maybe it's just used on its own to try to study that material in more depth. And we also, again, develop different types of systems. They might be diagnostic systems for things like malaria detection or cancer detection, or more recently, given the current pandemic, we also have kind of moved into the field of UVC disinfection, specifically trying to work at developing low-cost disinfection methods. And all of this work kind of fits into 2 general areas. The first is looking at integrated photonics, specifically nonlinear integrated photonics, as well as developing kind of more integrated systems. And the second is healthcare and wellness. Today I'm focusing obviously more on the first topic, but if you have questions on the second, you should feel free to ask. I believe I have some backup slides at the end, so I could answer those questions as well. So again, today I'll first give a brief overview of resonators as well as surface chemistry, because we do use surface chemistry in making these types of nanomaterial enhanced devices. And then I'll talk about 3 specific projects that we've been working on. The first are Raman lasers, which many of you are very familiar with, then photon pair generators, and then a brief overview or preview of 2 types of photo-triggerable devices, which we just had a paper come out actually last week on. So what is an integrated optical device? So it's simply a device that has a lot of discrete components integrated onto a silicon wafer. And these components can be things like resonators or couplers. And depending on the actual function of the device, the specific combination of devices can be oriented or combined in different manners. And the role that the discrete components, like the ring resonator, plays can be very different, depending on if you have the rings combined in a linear array. They might be used as a buffer. If you have just a single ring, it might be used as a filter. It could also be used as an amplifier, as the foundation of a laser. So depending on your specific configuration, you can create many different systems. Today we're going to focus mainly on resonators, but our group has worked in a lot of different types of systems. But again, we focus mainly on optimizing the individual components, and we usually collaborate with groups when we want to create a larger system or characterize a larger system. So what is a resonator? Specifically, what is a ring resonator? So they're actually a whispering gallery mode structure, and whispering gallery mode structures simply confine light in circular orbits, depending on if they're on resonance or off resonance. In other words, if they're confining light or not confining light, that will depend on the exact geometry, the refractive index, and the specific wavelength. If they're able to confine light, then you're able to get optical amplification. The first whispering gallery mode resonators and optics were actually perfectly spherical suspended droplets in vacuum, and they were suspended based on the optical trap. So it was basically a liquid droplet being held by an optical tweezer. Light was coupled into it using a free space laser. So these were very delicate experiments. More advanced experiments were, quickly followed using silica microspheres and crystalline microspheres, which provided a much more stable platform to perform more advanced experiments. One example is shown here. It's a rendering. It's a simple silica microsphere on the end of an optical fiber. And you can make these types of structures using fire, using a flame, using a laser, by simply melting the glass. And then based on thermodynamics, they reflow and form a sphere. And more recently, these types of structures have been made out of pretty much all optical materials of interest. This is just a subset. It is by no means comprehensive, but they're made out of silicon nitride, diamond, silicon, the fluorides, so magnesium fluoride, calcium fluoride, silica. They're also made out of carbon, so many different material types. So in our group, we work mainly on silica, silicon nitride, and silicon oxynitride. And then we use those platforms and try to improve the properties or modify the properties by combining additional materials, whether they're polymers or organic materials or 2D materials, just to try to tune the specific nonlinear coefficients of kind of those platform or basic materials. So one of the key figures of metrics of a whispering gallery mode cavity is something called the quality factor, or the Q. The quality factor describes how long the device can store light. And one way of characterizing it is by that specific resonant wavelength divided by the full width half max of that resonance. This is directly proportional to the photon lifetime inside the cavity. However, the easiest way to actually experimentally characterize it is by measuring that resonant wavelength by using a tunable laser and scanning across all the resonances of the cavity, and then you get a spectra and you measure the line width of the cavity. The reason why Q is an important metric is because it's used in the calculation of both the circulating optical intensity and the circulating optical power. And both of those determine the intensity or that amplification of power that your resonator can give you. Obviously, there are many other metrics of interest. So there are things like the optical mode volume, the finesse of the cavity, but Q kind of underlines or underpins all of those other metrics. So it's usually the first metric that you measure after the resonance wavelength. And these devices have been used in a lot of different applications, quantum optics, diagnostics, communication, as well as nonlinear optics. Today we're focusing on nonlinear optics, but they've been used in a lot of different fields as well. So within that broader field of nonlinear optics, a lot of different nonlinear phenomena have been investigated. So stimulated Raman, third order harmonic, four-wave mixing, to photon absorption, cross-phase modulation. And one of the reasons why all of these different nonlinear phenomena are possible is because of their very high Q. So when you have a very high Q, you need a very low input power in order to generate nonlinear phenomena. So whispering gallery mode devices give you a very good test bed to actually access all of these behaviors. We're going to focus mainly on four-wave mixing and Raman today, but a lot of these other behaviors have been studied using these devices, and especially using some of the other materials that have, for example, very good two-photon absorption. One of the reasons why whispering gallery mode devices are a very interesting platform to combine with a surface coating is because that circulating optical field isn't confined entirely inside the cavity. So a little bit of it leaks into the environment, and this is called the evanescent tail. So anything you put on the surface will directly interact with that circulating optical field, and because the optical field is very intense, it will actually have a very strong interaction with that circulating optical field. So this series of pictures, the first one shows a colored SEM image of a whispering gallery mode resonator. The second is a cross-section of a finite element method model of just that toroid part, showing the location of the circulating optical field, identifying where the silica toroid is, as well as where that silica air boundary is located. And then the white dashed line is a cross-section through the highest intensity region of that optical field. And then the cross-section part is plotted in the graph on the far right, highlighting where the silica air boundary is. So as you can see in the graph, while the majority of the field is located in the silica, that little red tail is actually what's at the silica air interface and located entirely in the air. And the shape of that evanescent field and the exact quantity that's located in the air is going to be dependent on the refractive index of the silica and the refractive index of whatever is attached to the surface. And I would say whatever the refractive index of the air is, although air is not really changing. So there are lots of different possible nanomaterial systems that one could investigate. You could think about looking at different types of small molecules, different types of nanocrystals, plasmonic materials, different types of Chi3 and Chi2 molecules. We've looked at pretty much all of these. Today I'm going to focus mainly on Chi2 molecules as well as reactive materials, so small molecules that can actually change their configuration when they're triggered with light. But a lot of these different materials can be investigated. So a brief overview of some of the past work that has been done using silica cavity Raman lasers. So previously, researchers have shown that using silica cavity, whether it's a microsphere or a microtoroid, if you put in very low amounts of power, so in the microwatt range, but if you have a high enough Q, you're able to get Raman with very low thresholds. And this is notable because silica has a very low Raman gain, but you're able to overcome this low Raman gain because of that very high quality factor. And these are just two examples showing the single mode Raman emissions as well as the threshold from both devices. So what we wanted to do was to see if we could modify the surface, so create a structured surface that would allow us to improve the Raman gain of the system by basically creating a nanostructure or a nanocrystal on the surface, and therefore increase the Raman gain, but still maintain that very high Q factor. And in doing both of those, we would be able to decrease the threshold as well as increase the efficiency of the system. So those previous devices typically had efficiencies in the 4 to 6%, so very low efficiency devices. Additionally, by increasing the efficiency, we should be able to get anti-Stokes. So not only get emission at a higher wavelength from the pump, but also at a lower wavelength from the pump. So we tried two different surface chemistries in addition to the primary surface. So normal silica device, your surface has something called hydroxyl groups on it, which are just OH bonds. Now, if you nanostructure the surface by doing a very simple surface chemistry called a silanation reaction, we can then create a very structured SiO-Si bond. And we looked at two different surfaces. In the first one, we had an SiO-Si bond that then had a second methyl group on there. And in the second surface chemistry we looked at, we added two methyl bonds to that SiO-Si bond. And these surface chemistries are covalent surface chemistries, so they're permanently anchored to the surface. The importance of this surface chemistry, or an important feature of this surface chemistry, is that the SiO-Si bond has a fixed angle. The vibrational angle of this bond is 120 degrees, and Raman has a polarization dependence, and it's governed by that binding angle. So therefore, depending on which input polarization of light we used, we would expect there to be a difference between the efficiency of our Raman lasing. So we would expect there to be about a three-time enhancement between those two polarizations. So that would give us an experimental way to probe if the enhancement we're really seeing is due to that surface chemistry or due to some other factor or feature in our device. So the first thing we did was to verify our surface chemistry. So our initial silica surface had a very classic silica XPS spectra. The addition of the second layer, when we did a control layer, where instead of having a methyl group, we put on a chlorine functionalization, because chlorine would give us a very distinct signal. We were actually able to very clearly see the addition of that chlorine peak. We also did a Raman measurement using FTIR, and when we did the Raman measurement, we saw the addition of the methyl group. So we saw the presence of the CH3 bond. So in both cases, we were able to verify that our surface chemistry actually worked. To characterize the devices, we used a tunable laser. We actually used 765, 1300, and 1550 nanometer lasers. We then ran our laser through a polarization controller so that we could look for that polarization dependence. We coupled that into our device using a tapered optical fiber waveguide, and then the output signal was split between an oscilloscope so that we could measure the Q factor, and between an OSA or optical spectrum analyzer so that we could measure the output spectrum. Being able to simultaneously measure and monitor the quality factor and detect the spectrum is an important feature because it allows us to look for any kind of variation in Q during the measurement and confirm that our resonant wavelength isn't moving. And the coupling gap between the waveguide and the device is accurately positioned using a nano positioning stage so that we can maintain constant coupling. So the first thing we did, again, was to measure the quality factor. We actually looked at 2 different device sizes. So we looked at devices that had 53 microns and 83 microns in diameter. Because that circulating power is dependent on device diameter, we wanted to make sure that the device diameter wasn't an additional confound in our experiment. So that wasn't, playing a role in our experimental results. And we measure the quality factor at both polarizations. So as you can see in the data, the polarization was not playing a role, or at least not a significant role in our quality factor measurements. Additionally, the device diameter wasn't playing a significant role in our quality factor measurements, and both of these statements you would expect to be true. Additionally, the surface chemistry wasn't significantly changing our quality factor. So all of our Qs were kind of in the upper 10 to the 7 range, which means we can directly compare the devices because they all have very similar quality factors. Then we took broadband spectra to identify the free spectral range, and the 2 polarization states have the same free spectral range but distinctly different resonant wavelengths, which is kind of classic behavior. You expect this. Then we looked at the Raman lasing performance. So all the subsequent measurements were done at 765. So the first 3 spectra on this slide are showing the Raman lasing measurements of first a silica device, then a MS-coated device, or a methyl silane-coated device, or a dimethyl silane-coated device. For plotting in power, it's not immediately obvious that there's an improvement in emission intensity at the methyl-coated and dimethyl-coated device. So then we plotted it with the power as opposed to a dBm on the y-axis. And then it becomes very apparent that there's an improvement when you plot, when you have a methyl or dimethyl coated device. Additionally, the Raman shift was nearly identical, which indicates that it is that SIO-SI bond that's generating the signal. When we plot all of the data from all the devices, you can see that the Raman shift is nearly identical. Additionally, this Raman shift falls within the expected range for the SIO-SI bond, which indicates that this is exactly due to that surface chemistry and not due to some other phenomena. Now, this change between the OH and these 2 additional surface chemistries is about 40 times larger than a silica device, but this is a single data point, right? It's just with 1 input power, and it also can't give us something like the threshold or the efficiency. So characterizing those 2 values were the next step. So we took threshold curves at both polarizations. So when you have just a normal silica device, there's no difference in the 2 polarizations, which you would expect because silica doesn't have any kind of order to it. And additionally, the efficiency is incredibly low, which is what has been seen in all previous work. When you have the methyl and the dimethyl groups, you see a significant increase in efficiency with either input polarization. Additionally, you do see that threefold increase with one polarization over another polarization. And you also see a change in threshold. And we can plot this out explicitly, summarizing all of the devices we studied. And you can see that depending on which diameter device, you see a significant increase in efficiency. Additionally, when you look at threshold power, you see a significant decrease, about a factor of 2 in threshold power. And you can plot threshold power either as threshold power or circulating intensity, depending on which metric you're more comfortable with. And then the last step was to look at the role of the CH, right? Is there a CH vibrational activity? And we actually didn't see any kind of signal from the CH. So this is a pair of spectra. The first is looking at the signal from the SIO-SI bond, and the second is trying to find a signal from a carbon-hydrogen. And we would anticipate that the carbon-hydrogen or SiCH bond would be somewhere around 980. So in this case, we actually put in about 5 milliwatts of power, so an order of magnitude higher than we'd injected with any of the other devices, and we never could see any kind of signal around 980. And the reason is that this methyl group is actually completely disordered, much like the silica toroid is disordered. However, it's also located very far out in the evanescent tail, which means it's seeing a very weak amount of power. So that combination means that you actually are never able to get any kind of signal from that methyl group, which means the methyl group isn't playing a role in the signal generation. But that's an obvious question that I frequently get. So now, the next step is, is there cascaded emission? If we're getting significantly higher efficiency in the first peak, can that generate cascaded emission? And the answer is yes. So we clearly get cascades in the methyl group, and we get cascades in both the methyl group at both polarizations. So this is comparing the silica group, so just the normal silica surface, with both methyl polarizations. Additionally, we get anti-Stokes generation. And we're never able to get anti-Stokes generation in just a silica device at the input powers that we studied. So when we look at the cascaded emission in a little more depth, and we take threshold curves of each one of those cascades individually, so first order, second order, third and fourth order, for both silica devices as well as the functionalized devices. As the Raman order increases, the threshold power required for the silica devices, which is this black line in the bottom, significantly increases. Both it starts off at a higher power as well as it increases at a much faster rate. In contrast, the threshold power requires as well as the rate at which it increases is significantly lower. And then the efficiency is both much higher for both of the methyl groups as well as for either of them as compared to the silica surface. So basically, it's mirroring or mimicking the same behavior that we saw with just a single Raman peak. And then similarly, if we compare all of the devices we made as opposed to just a single device, we see the same behavior. So the threshold power for that first peak looks the same across all the device types. And this is important because it simply shows the reproducibility of this device. We weren't just measuring one device and seeing the same performance. So moving on to nanomaterial type systems and looking at both switchable organic materials as well as highly nonlinear organic materials. And one application that researchers are really interested in looking at right now are frequency combs and making very, very, very broad spanning frequency combs. And to do this, you really need, two components. You need a high power pump source and, highly nonlinear Kerr medium. And the goal is to initiate four-way mixing and then generate a lot of lines. And one way researchers are doing this is to make a device that has a really, really, really high Q factor, solve a dispersion problem in order to get a lot of comb lines. We decided, after looking at this equation, that we were more interested in addressing this little gamma term in the bottom, which is actually the gain. So if we can, maintain the quality factor, or at least keep it stable, yet address this gain term, then we could get similar performance. So basically change it from being an integrated device problem to being a material science problem. And there's actually been a lot of work done in organic chemistry looking at making really high performing Chi3 materials. And they've actually been studying it in terms of, trying to make parametric materials, doing all optical modulation, and they've done a little bit of work in doing entangled photon pairs with gas phase. So we were interested to see if we could take all of that knowledge and then translate it to having an integrated device on a chip. And just for some comparisons, so silica, silicon nitride, calcium fluoride, and diamond are all in the 10 to the negative 20 meters squared per watt in terms of their Kerr coefficient. In comparison, some of the high performing organic nonlinear optical materials are in the 10 to the 3 times 10 to the 5 times 10 to the negative 20 meters squared per watt. So they're significantly higher Kerr coefficients, which kind of gives you a little bit of a buffer when you start developing a device, right? Even if you degrade their performance, you still might have a higher performing device. So for first kind of exploration, we decided to use microspheres because they're much larger, much easier to use, much easier to a surface chemistry on. So if you start with your initial silica device, then coat it with a silane chemistry, leaving a reactive chlorine group on the surface. We then anchored something called DASP, which is a pyridinium-based nonlinear material, onto the group. Now this step was very critical. So having this ordered monolayer on the group is very distinct from doing something like spin coating or dip coating, where you end up with a disordered monolayer that is perhaps multi-layer, so not a monolayer. So when you're looking at the nonlinear behavior of organic small molecules, their nonlinear coefficients will change depending on how the molecules are oriented with respect to each other. So if the molecules are stacked parallel to each other, you can get very high nonlinear coefficients. But if they're stacked perpendicular to each other and they directly interact with each other, then you can end up with very low or even non-existent nonlinear coefficients. So developing a surface chemistry that maintained order was really important. Then we characterized them using a very similar setup. And throughout this process, throughout this surface chemistry process, we were able to maintain the Q factor. There was a little bit of decrease after we did the last step of the surface chemistry, but we still had devices in the mid 10 to the 7 to low 10 to the 8th range. And oh, there it goes. It just took a while to load. Okay, so when we look at the spectra, when we have a bare silica device and we input anywhere between 0.3 milliwatts to about 1 milliwatt, we were unable to see really clear four-way mixing. We got a lot of Raman generation, lots of Raman generation. depending on the stability of the coupling, so how much thermal vibration we saw, the Raman could end up getting really messy. So one of the challenges with microspheres is that because they have a lot of modes and a lot of very dense modes, every one of the internal resonance modes can generate a distinct Raman signal, and that's why you end up with Raman spectra that look like this. In contrast, once we had the DASP layer on there, we ended up with incredibly clean spectra. And the reason why the Raman ended up being quenched is because the increase in that Kerr coefficient made the Kerr process much more favorable than the Raman process. So the majority of the power went into the four-wave mixing process. And note this is going all the way up to 1.55 milliwatts, and we still aren't seeing any kind of Raman behavior. And additionally, we started seeing four-wave mixing at 0.5 milliwatt. We can then take thresholds of both devices. Our threshold was around 0.5 milliwatts. In contrast, for a bare silica device, you can say we kind of began to see a threshold, but really it's very noisy. I wouldn't really claim a distinct threshold in these devices. But most importantly, we were able to actually get very, very, very clean signal and idler generation. So what was interesting in this project is our initial goal was to try to create very large frequency combs. But in the end, what happened is that because our dispersion changed, we actually ended up making combs, you could call them combs, that looked like this. So they quenched very quickly because our dispersion changed very quickly. So this made a device that was very, very effective at making photon pairs at very low input powers, but really only made single photon pairs, right? It was unable to make large combs. And importantly, it was able to make photon pairs that had fairly large spectral separation. And making photon pairs is also an area of interest of a lot of researchers, more fundamental physics researchers. And this device is able to actually solve this challenge. So we're now working with a lot of physicists, essentially just making this device and sending it to them, which was an unanticipated benefit of this project. So to all the grad students out there, sometimes your research goes in new directions that you don't anticipate, and don't try to force it. It can be a good thing. Okay, so then the last project is looking at photo-switchable molecules. So in a resonant cavity, you can tune the resonant wavelength by tuning either the refractive index or the device radius, because the resonant wavelength is governed by the device radius and the refractive index. So a change in either one will tune your resonant wavelength. We decided to coat the device with a molecule that can change its conformation based on some density functional theory calculations. The refractive index change due to molecular reorientation was around 10 to the negative 4 times the specific wavelength we were testing at. The radius change that was induced was around 10 to the negative 5. Therefore, in our system, this resonant wavelength change was really dominated by the refractive index change. The specific molecule we were looking at was an aazobenzene group. This is the specific molecule. The switching or conformational change group is shown in red. When we anchored it to the surface of the cavity, it's anchored perpendicular to the surface of the cavity. And when we expose it to blue light, it actually collapses or folds onto the surface of the cavity. And then when we expose it to heat, it unfolds. And it's a reversible process. Because this is an actual physical change, we can't just attach a single molecule onto the surface. We need to include spacer molecules so that we give this molecule the room it needs to actually perform this folding and unfolding process. So this is the molecular structure. So when we hit or shine blue light onto the device, it goes from being this completely planar structure to being a folded structure. And when we expose it to heat, it unfolds again. We did this switching process by actually exciting the device with a 1550 laser and a blue laser that were simultaneously coupled into the device with a single tapered optical fiber waveguide that we developed and fabricated in our lab that was able to couple in both wavelengths. So as you can see in this first data set, when we exposed it to 410, we got a negative blue shift. When we exposed it to 10.6 microns, so it's a CO2 laser, we were able to thermally heat the device surface, which initiated the red shift, and then it recovered when it was able to relax back. We were able to do this on the same device multiple times. Additionally, one of the concerns you have with a organic molecule is its stability in air. Organic molecules are notorious for degrading over time and when stored in air. So this is a pair of results that we took. The black is the initial results, and the red is after we stored the device in air for 6 months and then retook the data, and we got the same results. We then made a series of devices where we varied the ratio of the methyl group with the photo-switchable molecule. And we showed that we could actually tune the response we got, and that the tuning actually varied linearly over the scale that we studied. And that if we didn't have any kind of photo-switchable molecule, we basically didn't see any kind of response. And then when we compared, the response that we got or we achieved with a control system that we did with an ellipsometer, we got very similar results in terms of scaling. So briefly in conclusion, because I want to leave time for questions, so we showed about a 10x improvement in efficiency, polarization-dependent behavior, and threshold decrease with a simple surface chemistry, and we achieved cascaded Raman and anti-Stokes efficient emissions using that. And we also demonstrated photo-switchable devices and photon generation using organic molecule-based surface coatings. And all the papers are on my group website. And again, I just want to thank all of my students and all of you for listening. And I'm happy to take any questions. And I'm going to leave my slides up. Yeah, just in case there are questions on specific slides. So, please.
Thank you, Professor. Very talk. Now I will request Palak to kindly take the question answer session. Palak.
Yeah. Good evening, everyone. So we are starting with the question answer section. So the first question is from Vikas Mishra. He is asking that what are the characteristics of typical modes in silica nanomaterials? Are they meridianal rays?
So the characteristics of modes in resonators they're usually Lorentzian. Is that what is being asked?
He's asking that what are the characteristics of typical modes in the silica nanoparticles? Are they meridianal rays?
Hold on. I'm going to go, give me a second. Because I have that nice broadband spectra, and I think that'll be helpful in this discussion.
Okay.
Here we go. Can you still see my screen?
See you.
You can see it? Yes. Okay.
Yeah. Q factor.
So, yes. So the characteristics of modes, they typically have kind of a characteristic range. Usually you have a fundamental mode as well as higher order modes. Usually you can get the highest circulating intensity or highest circulating power inside that fundamental mode. The reason you can get the highest circulating power inside that fundamental mode, so this is a finite element method modeling of a fundamental mode. So a fundamental mode has all the power isolated or focused in a single point. A higher order mode will have a distribution, not a single fundamental mode. So when you're testing, you always want to locate the fundamental mode of the resonator. And then the reason why whispering gallery modes, as well as other types of resonators like photonic crystals, are able to access nonlinearities is because if you look at like this equation, the circulating power is proportional to the quality factor. So if you think about it, if you have a quality factor of 10 to the 8th and you put in a milliwatt of circulating power, you're going to get your input power amplified by 10 to the 8th. So you're going to get like a significant amplification of even a very low input power. Similarly, your circulating intensity, if you have a very high quality factor, you can end up with like gigawatts per centimeter squared in circulating intensities, even with a milliwatt of input power. So those are kind of the usual metrics when thinking about these devices, because they're micron squared or micron diameter type devices. So they're very small, so they can have hundreds of microseconds of photon lifetime, which can be meters of circulating distance inside that type of device. I hope that answers this question. I really do. This is the worst part of online, because I can't see people's faces.
The next question is from Deepak Kumar. Evanescent waves are transmitted waves concentrated near to interface. What is that makes possible they stay near to boundary?
So the evanescent wave is being confined at the interface because of the refractive index contrast. So silica has a refractive index of like 1.4. Air has a refractive index of 1. I think it's actually like 1.0014 or something. But let's just go with 1. So the majority of the mode will be confined in the silica device. Now that assumes that your silica device is large enough that you don't end up having issues confining your light inside the device. So this in whispering gallery mode devices is often known as total internal reflection losses. In other words, your light leaks out, or whispering gallery mode losses. So if your device becomes too small, you will have problems confining the light. So that's why there is a calculation that we perform to ensure that our device is able to confine the light. In silica devices, the threshold is about 30 microns in diameter. That's a known threshold. It's kind of it's common knowledge in the field, but we can calculate it. There are analytical calculations we can do. If you change the wavelength, then that value changes. But 25 microns is a safe, 25, 30 microns is a safe bet. If you want to maintain a Q over 10 to the 8th. I can give a paper on it. It was by Olchenko and published in 1996 in Optics Letters. It's been cited like 10,000 times or something. Life goals.
Okay, so next question is again from Vikas Mishra. how one may create high nonlinear medium in these assembly of nanoparticles. What are typical composites like for four-way mixing?
Yep. So that's a great question. So there are like general rules. So for example, if you look at this molecule, it has what's called a very conjugated backbone. So this means that it can have an actual resonance structure along the backbone. So if you think about this in terms of an EE, you can get electron, they call it sloshing. So you can get electron sloshing along the backbone. So whenever you have a double carbon bond, your electron can like hop in between this carbon and this carbon. Benzene rings are resonance structures. So even though we usually draw benzene rings, like we being like the, I don't want to say general public, but the scientific community usually thinks of benzene rings as being this type of static structure. If you talk to a chemist, they usually draw a benzene ring as this, hexagon, but then they will draw a circle in the middle, because that circle shows that those bonds aren't static, so they can move within that benzene ring. So it's a resonance structure. So having this resonance structure next to this resonance structure means that all of those electrons can move back and forth, creating a very dynamic system. Right, so you have this resonance structure, this resonance structure, this resonance structure. This nitrogen is actively charged, right? It has a positive charge. So this whole thing is basically a gigantic resonating dipole. So this was one of the first, highly nonlinear molecules for doing nonlinear optics. There are obviously other ones, and it's a huge field. Trying to do predictive modeling of nonlinear optical molecules, because there are now some kind of general rules, like for example, creating something that has a highly conjugated backbone. But then, what if you put a metal in the middle? Because metals will give you lots of electrons. And then where should you put the metal? At what point do you have too many electrons? So anyway, so it's a whole field. It's a super exciting field. There's a lot of work being done in it because it has lots of applications in like molecular electronics and solar cells. Anyway, it's awesome. Super exciting. Clearly, I like it. This is really exciting.
So next question, how one may create high order in surface chemistry to achieve high nonlinearity?
So how we did it, so we were first inspired by this paper that came out in 2018, or no, this paper came out in 2008. So in this paper that came out in 2008 looked at how the different stacking of polymers and nonlinear polymers influence the direction of electron flow within the polymer. And they developed different ways of stacking polymers and different surface chemistries for creating polymer stacking. And then in our group, we had developed, our group and also in Ryan Bailey's group at University of Illinois, they had developed different ways of orienting small molecules as well as antibodies on the surface for biosensing. And if you think about it, it's the same problem, or like how do you create an ordered monolayer of a thing on a surface? And so using a silane chemistry is a very straightforward approach. And so a silane chemistry, you basically take this hydroxyl group, this OH group, and oxygen can be very reactive. And so then you take this hydroxyl group, you then use a silane group, and silane groups you can buy from a lot of different vendors, and the silane will attack, so it will bond directly to the hydroxyl group and create an oriented group. So the chlorine won't bond to the oxygen, but the silane will. And then you develop your, whatever your third molecule is, your third functional group. and you develop it such that only the left side of the molecule will bind to the chlorine and the right side won't. And so then it's a self-quenching reaction. So you only get a monolayer and it only bonds in one direction. So you think of it, if you think of it like Legos or bricks or something like that, you design it such that it only wants to stack in one direction. So it's a lot of chemistry. If you talk to a surface chemist, this is really easy. It's a matter of figuring out and optimizing your surface chemistry such that your surface chemistry process doesn't damage your device. That's the hardest part. Because a lot of surface chemistry processes you can just do in a reaction vial with a magnetic stir bar. But if you put a silicon wafer in a vial with a magnetic stir bar, you end up with silicon powder. And that's not good. We lost a lot of devices that way. We made a lot of powder.
So the next question is again from Vikas Mishra. Can these photon pairs be used in quantum encryption?
Yep. So that is exactly what we're looking at, what we're trying to do. So we're working with a group in Mexico, and their research is focused on trying to characterize and do photon pair generation for quantum encryption. That's their thing. We don't have the capability or the testing setup to actually do those types of measurements because those are very complex measurements to do. So we're sending them devices and they're doing characterization. And it's working, but we don't do that. This is why collaborations are great.
Another question from Deepak Kumar. Why the response is polarization dependent?
Okay, great. Let me go to the schematic. Where is my schematic? Here we go. Okay. So the bonds are polarization dependent because the input light, depending on if it's going, so if I say that my light is going into the device this way and it's transverse electric versus transverse magnetic, it's going to be interacting with the device in one direction versus another direction. So it's going to be exciting that vibrational mode differently. And so if it's exciting that vibrational mode and it's the vibrational mode which generates the Raman emission, then you're going to end up with a different type, a different wavelength signal. So the efficiency is different because it is a vibrational signal. If it was an electronic signal, it would be different. You wouldn't have that polarization dependence, but it's a vibrational signal. And if you think about your excitation source as being directional, then depending on the directionality of your force, then it becomes polarization. I think that's the easiest way to explain it. It's a lot easier when I'm in person and I can draw. I think that's the closest I can get. I hope that helped.
The next question is from Vikas Mishra.
Mm-hmm.
What are typical characteristics of the organic chain molecules such that high nonlinearity is achieved?
I think I answered this. Maybe he could put like a smiley face or frowny face in the chat.
Okay, so next question is how one may find the nonlinear properties?
Yay, I think I got a smiley face. I can kind of see the chat. I think that's a smiley face. Okay.
So
Okay.
last question is how one may find the nonlinear properties.
So there are lots of different ways to find nonlinear properties. I would say if you just have a new material and you've just made a new material, the easiest way is to use a classic spectroscopy setup, which means you need a high power laser. So we actually just bought a high power laser in our lab, and everyone's super excited. So you buy a high power pulsed laser, which you're going to need usually like a femto or picosecond pulsed laser that can generate 15 to 50 watts. And then that's going to send a signal in pulses. And usually you're going to want to have some sort of polarization filter in there, maybe a paraquarter wave plate so you get a time delay in between the pulses. Then that is going to go into a photodetector, but like a spectrograph photodetector so that you can measure your spectral response of your material, plus maybe get things like photon lifetime being generated by your material. So they're very large optical setups to do basic characterization of material response. So we just bought a blue laser that can do this. Like it just came like 3 weeks ago. So we're starting to build one of these. Usually we collaborate with spectroscopists in the chemistry department. But since we've started making so many nonlinear materials in our lab, they've started kicking us out of their labs. So we built our own.
So now all the questions are over from the chat. So if anyone has any question, they can unmute themselves and ask.
No questions. Technically, we're over time, so I understand if everyone just wants to go and go eat.
Okay, thank you, Professor. It's a really nice question answer session. Now I ask Jacqueline to thanks our speaker.
Good evening. On behalf of CSIO SPIE student chapter, I would like to take this opportunity to express my heartfelt thanks to you, ma'am, for this very interesting webinar on the integrated nanomaterial photonic devices developed in your lab. So by using the characterization of organic molecules on whispering gallery mode resonators and thereby using it for nonlinear application in lasers, frequency comb generation gave a deep insight into the topic and your research. We are grateful to the speaker for being with us. It has been a great pleasure. We mention our deepest sense of appreciation who have directly or indirectly helped to make this webinar successful. I will now hand over the session to Keshav sir. Thank you very much.
Now I request everyone to please.
I think you're muted. Yes.
Thank you, Jacqueline, for the kind words. And now I request everyone kindly switch on their cameras so that we have a selfie with our speaker. Okay. On count of 3. 1, 2, 3. Thank you. I thank our speaker for this great talk, and I thank everyone from audience for attending this talk. I will also thank our advisor, Dr. Umesh Tiwari, for giving us these opportunities and resources. Thank you, everyone. This meeting is concluded. Thank you.
Thank you, everyone.